All right, so I'd like to thank the organizers for putting together this great event and for giving me the opportunity to be here. Yes, I'm going to continue with the theme from this morning. I'm going to talk about homological algebra, but for binary forms. And actually, let me start even before that. Let me start with the fundamental theorem of algebra. I'm going to work over the complex numbers. So I think we know that a polynomial of degree d complex coefficients has exactly d roots if you count them with multiplicity. So I'm going to write f of x as a d, x to the d, a1x plus a0. I guess I have to make the leading term non-zero. So what I'm saying is that this has d roots if you count them with multiplicity. So in other words, you can factor it as maybe the leading term is AD, and then you can group together the roots that are equal to each other, right? So just some factor beta x minus beta 1 with multiplicity lambda 1, x minus beta r with multiplicity lambda r, and I'm going to refer to these exponents lambda 1 to lambda r as a multiplicity sequence. All right, and so it's going to be a partition of D. Yes, without loss of generality, I can assume that this sequence is non-increasing. And the question that we want to address is, how does this multiplicative sequence affect the coefficients of the form? So more precisely, what are the algebraic relations that are imposed on the coefficients A0 through AD by the fact that F has a certain multiplicity sequence. So let me just say by the multiplicity sequence lambda. Okay, so we start off with some examples. Okay, let's take degree 2. X squared plus bx plus c, and let's take the partition lambda, just be a singleton. So I'm talking about quadratics that have a double root, and we know that this forces the following quadratic equation to vanish on the coefficients of the form. Yes? You could look at cubic forms now. And I guess in this case you have two interesting choices. So one would be to take the partition 2, 1. And then another one would be to take the partition 3. I guess this is case 2 prime. So in this case, I'm still talking about cubics, but I'm still looking at the condition that one of the root is repeated. And the case, well, it's a little bit more complicated, but you can write it down. So you get a degree 4 homogeneous equation in the coefficients of the form, which is of course the discriminant of the cubic. And I'm going to write it down in case you have not seen this before. Okay, so it's some homogeneous equation of degree 4. And if I want to have a triple root, well, that's going to impose more conditions on the coefficients. And so, for instance, you get the following three quadratic conditions on ABCD that are guaranteed by the fact that the form has a triple root. So b squared minus 3ac is 0, bc minus 9ab is equal to 0, and c squared minus 3bd is equal to 0. Okay? So anyways, you'd like to have such an understanding in general for arbitrary degree and for arbitrary partition lambda. One thing that maybe is a little awkward is this condition that AD is non-zero. If I make the coefficient AD equal to 0, then basically I'm dropping the degree of my binary form. So it's maybe slightly better to talk about this problem in projective coordinates. So my setup, which is part of the title of this talk, is slightly different, which is I'm going to work with homogeneous forms of degree D in two variables. AD x to the D minus 1y plus a0 y to the D. So I'm just homogenizing the polynomials I had from before.
Can I ask a question?
Yes.
So in your case too, when you have a double root and a simple root, so does that also include case 2 prime? So could you have the double root coincide with the single root?
That's right. So this locus is in the closure of that. Yes. So if I really want the multiplicity to be exactly 2 and 1, then it's going to be a constructible set. I have to take the difference of them. It's a very good question. So, question. Yes, there's a question. No, there are no stupid questions.
Well, I was asking Frank why you start with one equation, suddenly you go to 3.
That's a great question, and in fact, we don't understand what the pattern is. I give you a lambda, how many quadratics, how many cubic equations? And you'd like to make them in some sense. Yeah, so I'll formulate a question later, but it's a.
Well, I just point out that it's a higher codimension, and it's not a.
It's a higher codimension. I'll talk about that, but it's codimension 2.
I understand. Yeah.
So
and it's not a complete intersection.
And it's not a complete intersection, yes. But that doesn't tell us. That doesn't answer the question how many equations would.
But is there something like a sub-resultant that people have that does some of this?
I'm going to tell you what I know, and then we can talk during the group sessions on Wednesday through Friday about what.
I want to clarify what you answered the previous one incorrect, right? So when lambda has multiplicity 3, it satisfies 2 prime, and when it has the multiplicity 2, 1, or 3, it satisfies 2. Right.
When I have a root of multiplicity 2 and a root of multiplicity 1, then I get this equation. So in particular, this equation is implied by these 3. If I exercise.
Which is inside of the way.
So this degree 4 is in the ideal generated by this degree 3 quadratic equation.
Yeah, that's what I was saying. So
yes.
This one is precisely 2, 1. It means it's satisfied 2,
but not. That's right.
Yeah.
Yeah.
That's on the question.
So these are great questions. So I encourage everybody to join the tensor group because we're going to have more like this the next couple of days. Okay. So I said I want to work with homogeneous forms. So that, for instance, if I make AD to be 0, I don't drop the degree of this form. And then I'm going to study them up to scalar multiplication. Yes. So study such forms up to scaling. That's good. That really doesn't change the factorization pattern. And so more precisely, the parameter space for such forms is going to be the projective D space. Yes, if you want coordinates, you can think of the coordinates as just the coefficients of this form. Or another way you can say this is to think of the projectivization of the space of degree d homogeneous polynomials in two variables, which, by the way, these are called the binary forms, and they are symmetric tensors in two variables. So that's why I'm talking about this in the tensor group. Okay. So that's the parameter space, and what are we going to be looking at? We're going to be looking at the subset of those forms, which I'm going to write in this way now, with the property that they factor as L1 to the lambda 1, L2 to the lambda 2, Lr to the lambda r, and each Li is just some linear form. Yes, so let's say just linear. And if I want to get the closed set, I should allow the forms to come together. Yes, become equal. So anyways, I'm not requiring here that the forms are distinct, or they're distinct up to scaling. This is the definition of X lambda. Okay, so part of understanding this equation is I want to understand the ideal of all the functions in d+1 variables. So I guess I can write S for a polynomial ring in d+1 variables. So this is the coordinate ring on my projective space, and I'm interested in polynomials in this ring which vanish for every form with a given factorization pattern. I'm going back and forth between this coordinate notation and just talking about the form with coefficients A0 through AD. All right. And so the first thing to understand is, of course, the generators of the ideal, the equations here that vanish on my X lambda, and that generate all the polynomial relations between points on X lambda. But you could ask more generally to understand things like syzygies or Betty numbers. Yes. So the questions that we're going to focus on is to describe, for instance, minimal generators of this ideal, or more generally, syzygies or Betty, algebraic Betty numbers. Okay, so maybe we all know what it means to talk about generators. If you haven't seen Betty numbers, let me quickly give you a definition. So what do I mean by the Betty numbers of X? Well, this variety has a homogeneous coordinate ring. I take the polynomial ring and I mod out by the ideal of functions that vanish on X lambda. This is a module over S. So is the complex numbers if I think of the variables acting by 0, and then I compute the Tor group I. It's a graded module in degree I plus j. Oops, I skipped something. I have to take the dimension of this vector space over the complex numbers, and this is the Betty number Bij. Okay, and well, in this commutative algebra, we take these Betty numbers, we put them in a table, and we try to study the table. Okay, so so the Betty table, for instance, of X lambda Or I think of I as indexing columns, maybe J as indexing rows. And in here, I'm writing now the number Bij, okay? And so, you know, you have this, most of these numbers are zero, so this is really a finite table. There's refined invariance that you can consider. Refined coarser invariance, I guess. You can just focus maybe on the width of this table, and that's called the, maybe I'm going to refer to this as the projective dimension of x lambda. And the height of the table would be something that's usually called the Castelnuovo-Monfort regularity of x lambda. I'll give an example soon, but this is sort of what we are trying to understand when we study Betti tables. Okay, so let's do this example. So d equals 3, cubic forms. So we have a triple factor. So d equals 3 again. The partition is just lambda equals 3. And so it turns out that the Betti table in this case has a simple form, and then I'm going to try to explain the numbers. So if we means projective dimension 2, if you want regularity 1, and what are these numbers? Well, this one is very easy. It's just the statement that if I look at the coordinate ring of x lambda, that
Maybe
draw a line across the line. So I guess I don't have to explain this because I don't have enough space. I have enough space. Okay, I'll try here. So what this one means is questions. It means that simply that the coordinate ring is a cyclic module. So it's just that means that it's a quotient of the polynomial ring by some ideal, obviously. What is this 3? Well, this 3 indicates the number of generators of the kernel, the number of generators of the ideal x lambda. So there's 3 such generators, and they have degree 1 plus 1. So this is 3 minimal generators of degree 2. Well, this 3 equations, I guess I wrote them in wrong coordinates. I meant in terms of z0, z1, z2, z3, yes? Okay, and then what's this 2? This 2 says that the 3 generators of the ideal satisfy 2 syzygies, 2 linear relations. And I don't have space, so I'm just going to write one of them down. So the generators were b squared minus 3ac, and then bc minus 9ad. And audience participation, what was the third one? C squared minus 3bd. So there is a relation here with the linear coefficients. If I multiply this by negative c, I multiply this by b, and then I subtract 3a times the last one, then I get a 0. And that's responsible for one of the 2 here, and then there's another one. And that's the whole bit. Okay? So again, we'd like to do this in general, and if you want to help us, you can join our group. 0. Yeah, so that's what it means. It's a relation between these 3 quadrics that has polynomial coefficients of degree 1. And that tells me that these syzygies have degree 1 more than the equations. This is degree 1 plus 1, degree 2. This one's come with degree 2 plus 1, which is 1 more than that. You just plug it in. I mean, sorry, you expand the so you get 0. Okay, and of course, there's smarter ways of saying. Yeah. Everything cancels out. How do we find it? We use Macaulay 2. We write kernel, and you get 2 relations. Yes, or you realize that this is really a determinantal variety. This is the 2 by 2 minors of a 2 by 3 matrix of linear forms. And there's tricks you can play if you know determinantal varieties for writing down syzygies. I'll come back to that because we don't yet know that.
No, it's the rational normal curve section.
It's yes, but it's a special rational normal curve called the degree 3 one. which should be part of every talk in algebraic geometry or community function. Yes, called the. Okay, I'll tell you what it is called. So the point is that these numbers, they're interesting invariants, but they encode, further. So they look very algebraic, but they encode further geometric information. I'm just going to give you one example of how you get such information. So it turns out by keeping track of the entries in this Betti table, you can form a polynomial, which I'm going to just call B of t, just sum over all I and j, bij, I guess, of x. So I put an x here. I put a sign in front of it, and then multiply with t to the I plus j. So this is going to be some univariate polynomial that you can cook out of the Betti numbers. And what it is in our example is just 1 minus 3t squared plus 2t cubed. Okay, so how can you get some information about your variety from here? It turns out that this polynomial will usually vanish at t equals 1. So you could try to factor out 1 minus t as much as possible. And it turns out that in this case, you have a double root at t equals 1. And what's left is, I think, 1 plus 2t. Okay, so the information here is this exponent, which measures the codimension of x inside, in this case, the ambient space P3. So it's codimension 2. This is saying that x is a curve. Yes, of course, it's parameterized by P1, the linear form that you raise to the third power. But this also has some interesting information. If you plug in t equals 1, then of course you no longer get 0, because I extracted all the roots that are equal to 1. So in this case, you get 3. This 3 is the degree of x, is the number of points of intersection between x and a linear space of complementary dimension. So in this case, I have a curve intersected with a hyperplane. I get 3 points. So it's a degree 3 curve in P3. This is what's called the twisted cubic. Okay, so the twisted cubic is one of the examples of the varieties x lambda that we studied. Okay, so I don't really want you to think of this as a method for computing degree or dimension, but I want you to think of the Betti numbers as just maybe more refined invariants than the dimension of the variety or the degree. Okay, so, well, it turns out that if you only care about degree and dimension, then maybe you shouldn't join our group, because this has been known for a while.
Inclusionary, not exclusionary.
You can join our group, but maybe it's not going to be very interesting. So, is this include? So, I mean, maybe I should clarify. This is 87. So what does it say? It says that if we have a partition lambda 1 through lambda r, then the dimension of x lambda is r, of course, because there's the number of degree of freedom, there's the number of roots. Yes?
The question is whether you can also extract information from this Betti polynomial if you assign different variables to those columns, thinking of it as a bilinear.
So, if you separate I from j, then you'll actually cover all the code. So bilinear, you mean do instead of t to the I, t to the j, write xi times yj? But that's the same information, yes? And it's just a Betti table, yes. You can think of it as a generating. So you're losing information when you write down the form that I wrote down up there. It's usually not going to determine the Betti numbers. It's going to really determine alternating sums of Betti numbers along diagonals. So the Betti numbers are certainly more refined. I again, we can discuss more starting tomorrow. Okay, so I told you the dimension of x lambda is r. That's maybe not surprising. And then what's the degree? I don't know exactly what the best way to write it is, but it's r factorial divided by, I need to introduce these multiplicities, lambda 1, lambda r. So what is mi? This is the number of parts of lambda which are equal to I. So I think maybe for this purpose, it would have been better to express lambda as 1 to the m1, 2 to the m2, d to the md, by keeping track of how many 1s, how many 2s, how many d's there are. And this would make this product into 1 to the m1, 2 to the m2, d to the md. But anyways, there's a very explicit formula. I don't know what the best way to write it is. Okay, so we know the dimension and the degree. We don't need the Betti numbers to understand this, but maybe these Betti numbers tell us more refined, more precise information about. So the twisted cubic is an example, yes, but of a variety x lambda, but there's more examples that are perhaps familiar to you. So I can make this an exercise maybe. Example, you choose. So if I take the partition 2, 1 to the d minus 2, so this is dimension d minus 1 by Hilbert, and you can compute the degree, and you'll see that the degree is 2d minus 2. So this is the, in this case, x lambda is the discriminant hypersurface. Has degree 2d minus 2. So check that, plug it into your formula, in the formula up there, you get 2d minus 2. Okay, the rational normal curve, the generalization of the twisted cubic is the case where lambda has a single part. Yes, single part means dimension 1. And then this is a rational curve of degree d. But then perhaps there's other examples that are familiar. So if I take lambda to be d minus 1, 1, this would be an example. There's two parameters here. So this is an example of a surface. And what it is the union of tangent lines to the rational curve. So this is sometimes referred to as the tangent developable surface to the rational normal curve. Yes, I mean, again, from what we discussed earlier, since this, I guess this is a refinement of D, if I make these two parts come together, I get D, means that this variety is contained in here, and in fact, this is the union of tangent lines on the curve. So anyway, there's many interesting examples. And I guess I had, I mean, perhaps what you want to do is you fix D, you look at all the partitions, and then you try to understand these Betti tables.
So all of the examples right now are special cases of hooks.
So Wayman studied hooks, and there's one of the assigned readings for our group. It tells us something about the minimal equations, but the Betti tables are not known in general. So that's still an open case. It's not necessarily the direction I wanted to point to, but it is certainly something that we can discuss if you're joining us. So, I mean, if Wayman didn't do it, maybe we shouldn't try to. It's too ambitious, yes. So let me talk about d equals 4. I think there's more questions, maybe? More questions? So d equals 4, okay, we can list the partitions, I guess. Lambda, x lambda. So here you get the rational normal curve. 3, 1 is the tangent developable. 2, 2, well, this is some surface of degree 4, according to Hilbert's theorem. So I'm talking about forms that factor as product of two squares. There's the 2 on 1, which is the discriminant hypersurface of degree 6 in this case. And I never wrote 1, 1, 1, 1, but that's just because every form over the complex numbers factors as a product of linear forms. So maybe these, the first one, the last two are maybe more studied. So let me talk about this surface. So again, you write down Macaulay 2 and try to understand what the Beatty table is. And what you find is the following. So 7, 10, 5, and 1. So what happens in this case is that the ideal of equation is minimally generated by 7 cubics. And those have 10 linear syzygies, which have further syzygies and so on. Yes? And so you might want to try to understand explicitly what these 7 equations are. And you can. These are the 3 by 3 minors. So maximal minors of a 3 by 5 matrix of linear forms. You do a quick count, yes? 5 choose 3 is not 7, so you should be nervous.
No, because we trust you.
Frank's not nervous because the 10 minors are linearly dependent, and the space of minors is 7-dimensional. Okay, so and there's many things that maybe if you study determinative varieties in the generic setting, you'd find they're a little bit off. So the 3 minors of a 3 by 5 matrix, you expect to cut something out of codimension 3, 5 minus 3 plus 1. So it would be a curve in 4 space, but this cuts out a surface. Yes. So that matrix is very much non-generic. The length of a generic determinative variety would be 3. You would stop here. The even node cut complex for 3 by 3 minors would stop there. So this is something very degenerate. Yes. Yes, and we will discuss this in our. No, I will actually tell you a recipe, and I'm not going to write down specific entries, but I'll tell you how to construct it. Well, I'll come back to that. Okay. So the goal for our group is okay. Actually, we're not going to try to do the arbitrary lambda, but really the goal will be to understand. This is just the surface case. So just understand the case XAB, where of course it's a partition of D with 2 parts. So I'm talking about the surface. So the tangent developable would be one example, D minus 1, 1. But I want to try to understand all of them. Okay? And so let me tell you some of what's known. So in some work I did with collaborators a few years ago, what we did was to work out the tangent developable case, so D minus 1, 1. So what we did was to compute the Beatty table of XD minus 1, 1. And maybe I'm not going to tell you exactly what it is, but this was interesting. It's because this Beatty table is the same as the Beatty table of a general curve of genus D in its canonical embedding, and that's why we were interested in studying these tables. But it turns out that this is some nice varieties called Macaulay. Gorenstein has regularity 3, so the rows are 0, 1, 2, 3 in the Beatty table. We understand the entries, so we understand everything about this case. Yes. And so the other results regarding surfaces are by actually they're even earlier. So then what we did. So this is Abdes Salam. which delta T. So there's a series of two papers where what they show is basically that in the case where the two parameters A and B are the same, then this variety is too regular. So more precisely, the ideal is generated by cubics. And there's a linear resolution. So something like this. Yes, it's not an Egan-Northcott complex, but it's something like that. And then in the case where the parameters are distinct, then this is three regular. But the Beatty numbers are not understood. So for instance, not even the minimal generators. So the minimal generators have degrees, can have degrees 2, 3, 4, and maybe all the combinations. So for the tangent developable surface, if the degree is at least 5, I think it's the ideal is generated by quadrics. But in this more general setting, you can have just degree 4 generators, or you could have some of degree 2, some of degree 4. All kinds of possibilities occur, and we actually don't understand what happens. Okay. So, anyways, that's we start here. If we end it by Wednesday, then we move on to the general lambda. If we don't, maybe we continue. Okay, that's the plan for the week. Okay, so I guess that's the outline. I mean, just explaining what we're really trying to do. So these are also. These are two papers. They also use a lot of physics language, and I gave up long ago trying to understand physics language. So they're long, 30 pages each. So let me explain how I think about this case, XAA. And because that, I mean, you kind of understand if you know that's linear resolution, you find the cubics, and then you know the Beatty table. And so really this would be the difficult case. So the rest of the talk, I just want to discuss the case of this surface where the parameters are equal to each other. Okay, so how can you think of this? Well, there's a natural parametrization. Yeah, so I'm saying it's L1 to the A, L2 to the A. Well, but that's L1, L2, everything raised to the 8th power. So that's a quadratic raised to the 8th power. So what is this X? It's the image of a map from P2 to P2A, which takes a quadratic, I guess, F, and it raises it to the 8th power. So that's a parametrization. This map is just a linear projection of a Veronese surface. And it's actually an isomorphic projection. So the surface itself is just a copy of P2, but it's embedded by a non-complete linear series inside this big projective space, okay? And so, of course, if you have a parametrization, then there's a natural way to study equations. You look at the restriction map. So this would be, you look at polynomials of degree I on the ambient space, you restrict it to P2, and then you get polynomials of degree I times A. Okay, so this is just the restriction map coming from the parametrization. You could look at the induced map on global sections. And let me refer to this map as pi I. The kernel will tell you the equations of degree I. The image of the map will be the part of the coordinate ring of X that lives in degree I. Yeah, so understanding kernel, co-kernel of this map is easy. And so here's the general fact. This is just general nonsense about regularity that I don't really have time to explain, but to show that X is too regular, yes, too regular, and ideal of X is generated by cubics. And what you need to show is really that the map in degree 2, this map is an isomorphism. So what is this map in degree 2? Well, it starts off polynomials of degree 2 on sim 2a of C2, yes, on this space of 2a plus 1 coordinates of my binary form. And it ends up in sim 2a of sim 2. And it's enough to show that this map is an isomorphism. So we know abstractly that these representations of GL2 or SL2 are isomorphic to one another. This is an instance of Hermite reciprocity. But what we're saying is that this induced map realizes that isomorphism. So that's what we're trying to prove. So the question is, where does this come from? And it turns out that the fundamental object that controls just this whole, I mean, all of these maps and the variety X in this case is one of the three tensors that JM told us about on Monday. So sort of the key player is the following three tensor. So what's a three tensor? I have a map from one vector space times another, so bilinear, yes? So 2a C2 into sim of 2a of C2. Let me call this map phi. What does it do? Well, it inputs a pair of forms f and g, and the output is the Jacobian of f and g. Yeah, this is the determinant of partial derivatives, I think. That, yes. And here's a, I guess, Calc 3 exercise. That this Jacobian is 0, so phi of fg is 0, if and only if f to the a and g are proportional. So if and only if g is the image of f via this embedding of P2. So now what did JM teach us to do when you have a three tensor? Well, you can think of it as a family of linear maps. So you can think of this, for instance, on P2. Well, on P2, it's a family, so you're varying the form F, which is parameterized by P2, and you get a linear map. In this 3 by 5 A is 2. And it's not on P2. Okay, let's do the 3 by 5 matrix, which I conveniently erased.
Yeah, so I'm a little uncertain with numerology.
Look, so that's why I erased it, and it doesn't matter the numerology because I'm out of it. So let's do on P2A. A is 2, so this is on P4. So the surface in P4, yes? So, so I'm varying G. For a given G, I get the map from S2 to S2A, yes? So I get the map from S2 C2. I like to write P of minus 1. I guess I have a different twisting than JM, but other than that, it's the same. This is the map phi. What is it? It's a 3. This is dimension 3. This is by 2a plus 1 matrix of linear forms. So when A is 2, this is a 3 by 5 matrix, okay? So usually, yes, so how does this family work? If I fix G, I look at the map that sends F to the Jacobian. That's going to have maximal rank. It has no kernel, yes, unless G is a power of F. So this usually has maximal rank, but it drops rank exactly when G is a power. It drops rank along XAA. And so it's the 3 by 3 minors of these matrix that vanish and actually generate the ideal. Okay? So, mode of time? Yes. So the point is now that on P2, you can think of this as a map from sim to A of C2 to itself. And this map has constant corank 1. So what's the kernel of this map? So if you fix a point, if you fix a form F, a point in P2, the map sends G to the Jacobian. The kernel of that is exactly spanned by F to the A. So it's one-dimensional. It's a square matrix. The co-kernel is also one-dimensional. Okay, and so now, so what that means is that the kernel and co-kernel are line bundles, and it turns out that this is O of A, and that this one is O of minus A minus 1. Okay, and so now the next step is, this is what happens at the level of linear maps. You're taking the symmetric square of this two-term complex. That's gonna map onto O of 2A, and then the induced map from here to global sections of O of 2A has to be, is the map that we're studying. And I know Hal would have liked to see the spectral sequence argument. It's really easy. Most of the terms in that complex are going to be acyclic, and what's really going to happen is that the symmetric square of this and O of 2A are going to be cohomologically the same. Like everything else in the complex has vanishing cohomology, is acyclic, and that's where the isomorphism comes from. And there is no physics in that proof. It's just homological algebra. We'll try to do more of this for the rest of the week. Okay.